go for the second order system, which is more rigorous. And I think the majority of our practice or calculation will be on the second order systems. And here again, for whatever block diagram we would have, for whatever the system, the dynamic system here could be the motors and could be anything. And here is our transfer function, the final block diagram, and then we can get final one more step. Okay, so here is our example here. Assuming we are dealing with a certain block diagram like this, and here is very particular, we call the unit feedback system. And you might have other feedback systems. But anyhow, this is our demonstration for our textbook, from our textbook. And for whatever the dynamic system, if eventually your transfer function is like this, if your closed loop transfer function is like this, the denominator has the highest degree of 2, then this is defined as the second order system. And y, and again we can do this one. So here is y over r equal to whatever the constant. Here, for example, is omega m squared, and s squared plus 2 zeta omega ms plus omega m squared. So here we simply take the y over s and multiply will be equal to omega n squared times r over s. Here, s squared plus 2 zeta. Okay, so after taking the inverse Laplace transform, you can see basically this one is y double dot plus 2 zeta omega n y dot plus omega n squared y equal to omega n squared times r. So this one basically is you know that is a force function. External representing it is the external excitations. This one, you know, this one basically is a second order vibration system, okay, using our mechanical terminology. Okay, so that reason, as long as you can see this representing is any closed loop function, as long as that closed loop function has the highest degree 2 in the denominator, then that is the second order system. Okay. This second order system, for this is the generic template. That one is, in particular, is for this special example that is using for our demonstration only. So here, again, for the slides onward, we only stick onto this template. And that means if you like to plug in the equations, then you have to fit in your transfer function like this. If the transfer function have a different numerator, then you have to do the calculation from scratch, and which means take out the inverse Laplace transform, whatever you learned so far, and to repeat the calculation and then to fit in the corresponding requirement. Okay, I'm going to show that one. But anyhow, and keep that in mind for the discussions onward. Those are only particular for these specific second order systems, and the second order system would have the common terms, would have a common template as the denominator, because that always is a second order polynomials, but the numerator could be different. Okay, here is a little bit things, and I'd like to get your attention here. Okay, so with this one again. We have a similar way to try to do this one. So here we have a second order system, s squared plus 2 zeta omega n s plus omega n squared. So we have the second order system. We want to repeat the calculation for the unit impulse, unit step, and unit ramp. And we see what happens. And the calculation will be, again, here we are concerned about the transient response. For the steady state response, I think the homework, and again, this weekend you should be able to work on the homework on the second order system. So we have done that one. So here we're going to focus on is on the transient response. Okay. So the first one is with this second order system like this, we want to calculate unit the unit step input. So for example, here is a result 1 minus this term. Okay, and if you are taking vibrations, you must be familiar with these equations.
Yeah.
In particular, this term here and this term here, right? And in terms of the definition in vibrations, this is called the damped natural frequencies, right? And for this one, the question is, are you able to derive this form? Say, we can give a try. Let me try one. Okay, so here, let me try, say we try one example here. And instead of working on the symbols, and I think the textbook provides calculations in symbols, symbolic calculation to derive this one. But we don't have to, we can work on one example here. Say, let me make one. Okay, so for example, YOR equal to S squared plus 2S plus 5. Okay, so here is 5. So now if, say, when R equal to 1 over S, the unit step input, then we want to find the Y. Okay, so here we can see the Y basically is equal to 5 S squared plus 2S plus 5 and times 1 over S, right? And so for this one, if you want to do the calculation, then you can do it is this. And here we assume S squared plus 2S plus 5. Then say again A, B, S plus C. So we here come to our scratch calculations. So here we compare the both sides, and 5 should be equal to A times S squared plus 2S plus 5 plus B S plus C times S. Okay, so here we compare the coefficients A plus B equal to 0. S1, that means 2A plus C equal to 0. S0, that means 5 equal to 5A. So here we can obtain is A equal to 1, and C equal to minus 2, and B equal to minus 1. Okay, so hope my calculation is correct. If there's any mistake, help me. Okay. So minus 1 plus something like this. Okay. So here we can get rid of the minus sign, get the minus sign to here. So, and now, right now, I think you should be able to very good in this process. So here is S plus 1 squared plus 2 squared, and S plus 2. So you know you have to arrange into the certain form that can be take inverse log the plus easily. So for this first one is one of, the second one is we can put into this S plus 1 and minus So therefore, with this one, then we can get the YT pretty quick. That should be equal to 1 minus exponent minus t times cosine t, and minus 1/2 minus t sine t. Sine, sorry, qt, right? Okay. So with with these things, then if you like to put into the, with this one, say yt equal to e minus exponent minus t, and here is cosine 2t plus 1/2 sine 2t. So if you like to put into this template and say only have sine functions, so which means asking you to combine the both terms into the sine. So here is this. You want to get the form is this. You wish to obtain this one is equivalent to capital X times, for example, sine 2t plus certain phase angle. So if you want to be asked to put into this form, then the calculation is this. So from here, this one, we expand it. This one will be equal to x times, let me expand this one, sine 2t cosine phi, and plus cosine 2t sine phi. Okay, so here we compare the coefficients. So the coefficients of this term is capital X cosine phi, and that one, the coefficient of this term equal to 1/2. Then coefficient of the cosine is this, and coefficient of cosine equal to 1. Okay. So from these two equations, you can see that capital X squared is equal to 1/2 squared plus 1 squared. So therefore, the capital X will be equal to, this one is 4/5 here. Okay. And then also we take the ratio of the two. So here, let me say second term over the first term. So that means the capital sine phi divided by capital cosine phi equal to 1/2. This will equal to 2. On this side, this one equal to tangent phi. So from here, you can calculate phi equal to arctangent of 2. Okay, so here you have the capital, you have this one. So then you rewrite this, basically this form will be equal to this. Capital X times exponent minus t sine 2t plus b. So this one, basically in terms of our symbols, is like this. Okay, and in terms of the symbolic calculation, here we can see more the physical, the insight into the system here, because this one actually is defined as the damped system, and for this case, that should be equal to 2. Okay, and then the phi is defined as the phase angle. The phase angle actually, in terms of our calculation, that is exactly is this one. So here we can draw is this. If you are able to draw the force on the complex plane, so here is real and imaginary part. So here, if here is our complex conjugate two parts here. So from here, this is the second order system. The magnitude, the distance from here to here is omega n. Yeah. Good. Okay. This angle is cosine, a cosine of this one. So by this one, this definition is here. Okay. So here we mentioned the phase angle actually is the angle here. What is time now? 11:10. Yeah. Okay.
You took a little bit.
Good. Okay, so that is the meaning of the whole things. So the question, are you able to calculate yt as this? I think the answer now it should be yes, right? So here, if we're working on the numbers, that should be very straightforward. And if here we have the symbols, you can give a try. Okay, a little bit more rigorous, but the same step here. my suggestion is this. If you have the numbers and you can directly do the calculation, because you can see that won't take too much time. And if you want to plug in the equation here, you should be very careful, because these equations, and again, I can tell you, for many good equations, that shouldn't be the longer than 2 inch long. If any equation printed out in the textbook is measured longer than 2 inches, then that equation, once you want to apply, you should be very careful. You know what I mean? Because those kind of long equations are very complicated, and to me, they just simply is a symbolic calculation. They shouldn't be. Those ones shouldn't be given any equation numbers. The good equation should be boxed and that is a small box within a small box. For this one, if you want to apply, and then you should be very careful. And for this equation, again, that is based upon this form. Okay, if you the transfer function is not in this form, then if you plug in here, then you might have the mistake there. So here, we done this demonstration for this one here. Okay. Before we move on to the next page, then you might ask me, how can we do this one? So let me do the demonstration using the same example here. So again, if we have the same system, then right now the unit impulse, we have the S equal to 1. Then we can repeat the same calculation. So basically here, let me get rid of this one. Then we can redo everything. This one should be very straightforward. And for this one is S plus 1 squared plus 2 squared, the same thing. And here is 5. Okay, so to make up the things, then we can see this should be equal to 2 and then 5 times 2. Okay? So therefore, for this case, then we can see the y over t should be equal to 5 over 2 times exponent minus t times sine 2t. This one is very straightforward. Okay? So again, using these numbers, then I can say for the unit impulse, if you like, you can also do the symbolic calculation. This should be fine. Okay. So now we're back to here, and most of the second order systems are categorized by unit step input, because again, that is regarding maybe in instrumentation or maybe in other class, and we call this system identification. And to identify a system that have a few special techniques. For example, for the second order systems, yes, you can use unit impulse, but that won't give you too much insight into the system dynamics. From here, you can see for this case, if you're going to use the unit impulse and the system, say, for example, assuming, say, this board is second order system, then I can hit it, use the hammer to hit very quickly. Then the system with the board, if we can measure the vibration of the board, then at least you can see the damp. You can measure the damp frequencies. That's it. But for the second order system, if we give the unit step input, then you can look at this page. I believe you've seen this one in your vibrations. Again, this line marks our step input, okay, and that is the target the system tries to achieve. So this line extended potentially. So hopefully the system response eventually will go to this level, okay. And now the remaining is how fast and how the system approaching to the steady state value. Then you can see depends on the different damping ratio zeta. Then we have the system different response, right? And so those numbers are for the damping ratios. If damping ratio equal to 0, basically the system will oscillate perpetually and no going back. It's going to cross the command value, but we can see, for example, we look at this curve, the system without damping. So the system, okay, right now the system takes this command, and so it's going to rise up and try to catch up the input. Okay, it's give itself too much momentum, so basically overshoot. So overshoot, and then system eventually, because that is a feedback system. So the feedback system is negative feedback. The system going back to slow down its overshoot momentum, approaching to 0 and then coming back. Okay, now I'm overshoot. I'm coming back to our signal here. Okay, then his overshoot is correction of the overshoot again is too much, so it's undershoot. So basically, it's oscillating again and again. You know what I'm saying?
So it'll never catch up to the response soon?
Yeah. So you can see the system, the open loop system is this. Okay, and this is the feedback here. This is Y. So here we have the minus, we call the negative feedback here. This is R. So the system, once it's overshoot due to this feedback, the system would know I need to correct my overturned momentum. It's going to slow down. So once come over here, then for example, before the system catch up, you can see the value of Y is always the lower than C. The value of the output is lower than the command. So once it started before reaching here, then this value is always positive. Again, if we look at here, once the system started until before it reaching the target, this one is always positive. Once it's overshoot, then this value become negative, right? So this negative value will become to work on this one to have the system to coming back here. So the system once reach the certain 0 speed, and then we're coming back and here, okay? So it's overshoot, and again undershoot, and again that's oscillated. And if the system has a little damping, and for example, we can look at the 0.4 here. For 0.4 curve, because the system has a damping, so because of damping, the system will rise its value a little bit slower, but once you reach the value, it's going to overshoot, and again, but this overshoot won't be too big because of the damping. And again, this is an overshoot, then to this period, then the system begins to correct its overshoot momentum coming back here, and again, due to the damping take effective all the time. So here it's undershoot, and then but with an even smaller amplitude. So come back here is going to overshoot again, but here compared to this period with this one, you can see that overshoot magnitude is getting smaller. So here we can see the damping is sometimes good. It can help you the system to go back to come back to catch up the steady state value in certain way. Okay, but the damping is not good in the way is this. You can compare to the 0. The system can rise very quick. Compared to the damping, for example, 1 here, the system is going to rise slow, relatively slow compared to the lower damping ratio. Okay, so here I'm talking is kind of give you a hint of a few indices to categorize the second-order dynamic systems. And one is I give you right now is the rising, how fast the system response rise, and then how systems going to overshoot, and then the other things. So those are the features of the dynamic systems. And here you pretty much familiar with this curve, and here again it show up again. Here we draw the response of the system into here. This is a profile, and the system's oscillations are confined within the profile of the exponential decay here. And here is the oscillations. So here, this curve drawing is the system's response of the second order system here. And we want to know is how quick in the transient response, how the system is going to follow up to reach to the one domain. And here we're going to have the few
So on
labels.
your last page, because the error, I thought the error for a second degree system was 0 whenever you have a unit ramp input. So why can you have such a big error like with the oscillations, like on the page before this?
Unit ramp.
Yeah. Because that one with no damping, it has a huge error, like
Yes.
constantly. But I thought with the unit ramp input, the system was supposed to be able to catch up with the second
Yes.
degree.
Yes. For here, for example, if this curve corresponding to the zero damping ratio, and this one is right now, this curve is belonging to the transient response. However, we can also say this perpetually the steady state response for this one and will be the same as the transient response. So here, for this case, we can try to calculate steady state error, but that steady state error should be a function of time.
Yeah, it won't be 0.
Won't be 0, won't be constant, but should be a function of time. If you're interested, you can calculate. And how much? What is time now?
You have 4 minutes.
4 minutes. Okay, so probably Monday coming back here is we're going to introduce 5 measurements, 5 indices to characterize the transient response of the second order systems. And that is a way to design the dynamics. And again, that's back to our essence here. Control is to not only to understand the dynamic systems, but in a way, if we want to revise the dynamic systems, okay, and into the preferred the response. But in the first case is how can we define our preferred response, and that will be through the 5 indices we're going to design, we're going to talk about. Okay, so here is a little bit more, and I come back to my initial introductions here. Again, here that will be the very typical example using the second order system to, I will teach you how to modify. Okay, so coming back on Monday, and we will begin to this discussions here. Okay, thank you.